will be the workshop. I'd like to invite Dr. Dong Junjia to give us the forward. 接下来是工作坊时间，在工作坊开始前，我们将时间交由引言人，国立成功大学心理系龚俊嘉龚教授上台为我们引言。
So our second workshop will be given by Professor Liu. And I just talked to Daniel. He also just started learning R. The root was originally using MATLAB. So we'll have some first-hand or beginner learning experience sharing. And also, the code has been posted on our conference website, so feel free to download so you can try yourselves. Okay, so now let's welcome Professor Little.
Thanks very much. Yeah, as mentioned, all of my model fitting work was traditionally done in MATLAB. So when Cheng Tai asked me, oh, you can give a workshop in R on how to fit your models, I thought, oh, okay, that'll be interesting. But I worked hard to translate the MATLAB code into R. And I sent Cheng Tai the files last night so he could upload them to the website, but found an additional 4 bugs in the code this morning. So I will have to update those files so you're actually using the correct information. So this is going to be slightly different from the other talks that were given on systems factorial technology, because this will move away slightly from the non-parametric approaches that we've been talking about so far. Now, one question is, why would you want to do that? The non-parametric approaches are beautiful approaches to understanding what's going on. As Joe kind of hinted at, and as I talked about a little bit yesterday, and Mario talked about, there are assumptions underlying the techniques from systems factorial technology that sometimes might not come out in the data. So you could have violation of the stochastic ordering of the response times from different salience manipulations. So what do you do if you have a violation of the stochastic ordering? Well, there are a lot of different things you can do. The one I'm going to talk about is trying to understand what's going on by taking a parametric approach, starting with some theoretical assumptions about the underlying information processing model that might be going on, implementing them, and testing them that way. So you could set up, for instance, serial models, parallel models, and coactive models that implement the type of processes you think are happening when people are performing these problems, and use model fitting tools to test these models against one another. So it doesn't have the nice properties that the non-parametric analyses have. You don't get the nice qualitative distinctions between the models, but you can use some more quantitative tests to try to tease them apart. The other kind of more theoretically important property, I think, is something that Jim mentioned. You apply the sieve method, where you start with the non-parametric analyses to rule out entire classes of models. Then you can start asking questions about more specific mechanisms by adopting a bit of a parametric approach and building in some additional assumptions onto the standard models that are tested using the non-parametric analyses. So Mario Fific and I, along with Ron Mazowski, have done some interesting work where we had very good evidence that people were processing categorization stimuli that were comprised of 2 dimensions in a serial fashion. But we got even better fits when we assumed additionally that there was an extra attentional switch cost whenever they finished processing one dimension and had to switch to the other dimension. So by adopting this parametric approach, we were able to build in this attention switching cost and show that that even fit a little bit better than the standard serial model that we were testing using non-parametric analyses. We had another example. We had really nice looking data that looked somewhere in between a serial model and a parallel model. So we fit the SICs and they were mostly negative, but with a little bit of a positive blip. So it wasn't quite completely parallel exhaustive. It looked like there was a little bit of mix of serial exhaustive in there. So we were able to take a parametric approach and mix together a serial process and a parallel process to show that actually provided a better explanation of the data based on our model fitting tools than either one of those information processing models on their own. So the models I want to talk about are models that are really, Mario had a very large hand in building along with Rob Mazofsky, and I've been fortunate enough to utilize and work on as well, which combine elements of a lot of different theories that have been used to describe information processing. They really can be thought of as two parts. One part which has to do with the representation of the stimulus. And this is kind of the front end of the model. And that particular front end of the model is really based on the general recognition theory that Jim introduced yesterday. And I'll explain a little bit more about that in a moment, but the idea is that for each stimulus and each stimulus dimension, there's variability associated with the perceptions of those dimensions. And we can combine that type of representation with another assumption that is decision boundary theory, where we can carve up a categorization problem by introducing decision bounds where people will switch their decisions between, say, one category and another, and use this kind of carved up space to pull out the rate of evidence that an individual stimulus gives you, or the quality of evidence that each individual stimulus gives you for each of the categories. You can use that information you get from the stimulus representation combined with these decision boundaries then to drive sequential sampling models. And I didn't list all the references here because they're too numerous to put on one page. In the initial application of the logical rule models, we took that quality of evidence and just fed them into a random walk model. Now, a random walk model has the assumption, and perhaps this will make a little bit more sense in a few slides, that you're sampling from the stimulus, you're sampling from this variable, your perceptions of this highly variable stimulus, and if you if you sample some percept from this variable stimulus that falls into the category A region, your sequential sampling model will take a step towards responding category A. If you sample something from the category B region, it will take an opposite step towards category B. And you can use this framework to make predictions for response times. The novel thing that we did in our work was take all of these sequential sampling models and put them together in different mental architectures, so combine them either serial or in parallel, or just have a single random walk, which we assumed would represent a proactive process, and use different logical rules for combining the outputs of each of these these sequential sampling models to come up with the final distribution of response times. Now, in this presentation, I'm not going to use the random walk. I'm going to use the linear ballistic accumulator, which is another type of sequential sampling model or evidence accumulation model, which I'll describe in a moment. The reasons for that are not wholly important. The random walk model is a discrete response time model, so it takes discrete steps. Time is in discrete steps, whereas the linear ballistic accumulator is a continuous response time model. The similarities between these two models probably outweigh their differences in many cases, and you get away with using either one. I'm going to use the linear ballistic accumulator because it's a little bit faster to simulate from in R. So I'm going to apply these models to the particular categorization example that I talked about yesterday and that Mario and I applied, which is a category space where you've got 2 dimensions, which have 3 values on each dimension, which are combined to create these 9 stimuli. And then you carve up the space by introducing this L-shaped boundary here. So you've got one category, which I'm going to call category A, which is defined by this conjunction rule. So one of these items belongs to category A if it has a value on dimension x, which is greater than this vertical boundary, and it has a value on dimension y, which is greater than this horizontal boundary. And the other category is defined by the disjunction of these 2 rules. So one of these stimuli is a member of category B if one of its dimensions falls to to the left of the vertical boundary or lower than the horizontal boundary. So this is the categorization problem that I'm going to talk about and demonstrate how to fit these items. Our goal is to simultaneously capture the response time distributions from all 9 of these stimuli and predict very quantitatively and accurately the precise shapes of those response time distributions. So our theoretical assumptions are really combining a perceptual front end with a sequential sampling back end. So the perceptual front end is this general recognition theory framework. And this is going to give us how good evidence do we have for each of these particular categories. So if we have 3 values on a given dimension, and we just look at one of those, the representation, the general recognition theory representation on one of these dimensions, we might just set up a simple signal detection theory style setup. So I'm not dealing with the full multivariate power of general recognition theory yet. We're just dealing with a single dimension here. And we can look at one of the boundaries along that dimension. These are representations of 3 different stimuli, and the values of one of the dimensions from those 3 different stimuli. And the perception of those particular dimensional values is assumed to be noisy, so we represent that by a normal distribution. And the evidence that a stimulus belongs to one category over another depends on the location of this perceptual distribution relative to this boundary. So if we wanted to know, given this particular stimulus dimensional value, what evidence do we have that this belongs to category A? All we need to do is simply integrate under this function, which, because these are normal distributions, is actually pretty extremely easy to do. And that gives us a probability of sampling a percept from this dimensional value which falls into the category A region. So this is our theoretical assumption about the underlying process which is driving the categorization decision. Having some idea about how people perceive these stimuli, or some theoretical assumption about how they perceive these stimuli, the idea is that we use those samples that people draw from these dimensional values to drive a random walk process. So if I show you this particular stimulus, and you're sampling from a dimension X on this stimulus, most of the time you're going to sample a category A, or a stimulus value which falls to the right of this boundary and belongs to category A. So if you think about what's happening on a discrete step, if you want to give a descriptive analogy for what's happening in discrete time, in each step you sample a perceptual value from this distribution. If it falls to the right of this boundary, then your random walk process takes a step up. If it falls to the left of this boundary, and it will do that some of the time because some of this distribution crosses over there, you take a step down, and you keep accumulating evidence until you hit one of these thresholds. So if you hit this threshold, then you make an ultimate responsive category A. If you hit the bottom threshold, you make a responsive category B. The number of steps that it takes you to hit one of those boundaries gives you some estimate of the total time it takes to make that decision, or the actual decision time. The total response time then will be some combination of the amount of time it takes you to make the decision along with any other kind of non-decision time processes. Movement time and coding time are the 2 that are typically discussed. So in this categorization setup, we can think about 2 possibilities for how the dimensions might be combined. They might be combined independently, or they might be pulled together in a coactive fashion. If they're combined independently, then we assume that what drives the evidence accumulation rates on each dimension are the marginals of the bivariate normal distributions for each stimuli. So Jim talked about a lot of different possibilities and ways in which you could violate assumptions of perceptual independence and perceptual separability and decisional separability. I'm going to make things really easy for you guys and just assume that we have perceptual independence, perceptual separability, and decisional separability. So I'm going to assume that each of our stimuli here, represented by these bivariate normal distributions, all line up with each other. So we can just use the marginal distributions to as a representation for the perceptual values along each dimension. And I'm also going to assume that the decision boundaries are orthogonal to our dimensional axes. So we don't, we're going to ignore a lot of the complexities that are likely to really occur whenever you do these things to just simplify our discussion. So if we combine each of these dimensions independently, then hopefully you would have guessed by now that there are several ways we can do that. We can combine information from each of these dimensions in serial. So we might process dimension x first, followed by dimension y. And if we do that, if we process dimension x first here, you can see that for this stimulus, it's close to this boundary. So it's actually rather slow to reach threshold and make a decision. In comparison, on the y dimension, it's rather far from the boundary, so our decision on dimension y occurs very quickly. We accumulate evidence very quickly that this belongs to category A. The random walk races very quickly to that threshold. And our total decision time from each of these models is simply the sum of the time it takes us to complete each of these independent decisions. Alternatively, I should also remind you that you can feel free to interrupt me at any particular time in this talk if you have questions or you want me to explain something more detail. Alternatively, if we're processing these dimensions independently, that might also occur in parallel. So both of these random walks on each dimension race at the same time. For this particular item, because it belongs to category A and needs to satisfy both of those boundary decisions, the total time it would take you to make a correct decision is given by the maximum time that it takes you to finish these random walks. So our decision time here will be driven by this random walk of the maximum time, because this one takes you a little bit longer than that one. So we have multiple processing channels, one for each dimension in this case. This is two possible models that we could have. In this particular case, our processing models are both exhaustive. So we have a serial exhaustive model and a parallel exhaustive model. Alternatively, we could think about self-terminating versions of these models as well. For category A, because we have to satisfy both of these boundaries, in order for a model to do that correctly, it has to exhaustively process both of the dimensions. But if we looked at one of these category B stimuli, then a serial or a parallel model could terminate its decision after processing one of the dimensions and still make the correct answer. An exhaustive model would process both of these dimensions regardless of whether or not it was able to stop and make a correct decision. Alternatively, the decisions about each of the dimensions might be made holistically or configurally, in which case we're not going to use the marginal distributions to provide our source of evidence, but instead we're going to stick with that bivariate normal distribution and compute the area under this distribution that falls into the category A region based on both of these boundaries rather than one of the boundaries at a time. And whenever we do that, we get one source of the quality of evidence for category A, and it drives a single random walk process. And that single random walk process is what gives us our decision time. There's a single processing channel. Now, whenever you simulate a random walk model, or whenever you use a random walk model rather, there are analytic expressions or numerical expressions for generating predictions from these things, but they're a little bit messy. I'm going to keep things nice and easy by simulating from the model. If you simulate from a random walk model, that's a little bit slow. So I'm going to use the linear ballistic accumulator because it's a simpler representation about how these response times are generated. Now, it has different assumptions from the random walk model. The most important one is that in the random walk model, you've got perfect negative inhibition between each of your decisions. So if you take a step up towards one threshold, that necessarily means you're taking a step away from another threshold. In the linear ballistic accumulator, the assumption is that you've got two accumulators which are racing against each other, and a step up towards one threshold doesn't necessarily mean that you're taking a step away from the other threshold. In fact, the linear ballistic accumulator is so nice that you don't even need to go through this stepping process at all. It relies on a very simple property, which is that if we know, in fact, where we start our accumulation process, and in these models, the assumption is that we have one accumulator for the evidence for response A, and another accumulator for the evidence for response B. As we, our starting point on each of these accumulators is drawn from a uniform distribution. So we'll start somewhere between 0 and the top of the range of this uniform distribution. And we'll also know our rate of processing. That will be drawn from a normal distribution with a mean, which is determined by using this general recognition theory representation combined with this decision bound theory. So if we want to know the rate of processing this item for the category evidence for category A accumulator, it's simply the integration under this particular curve. So this green area here gives us the proportion of evidence that this particular stimulus belongs to category A. And we're going to call that a drift rate. And that's going to give us the rate at which we approach our threshold for responding A. Of course, we've got two decisions, so we're going to simplify things a lot and say that our rate of approaching response threshold B is just 1 minus this probability. So this would be the amount of area in that normal distribution which falls into the B region. So if we have, if we know where we're starting at, and we know what this threshold is, we know how much distance we have to travel, and if we know our rate at which we approach that distance, well, we can just rearrange the simple equation distance equals rate times time, and to get time equals distance divided by rate, to get a measure of how long it takes us to actually reach this threshold, given that we started somewhere here and we're approaching it with a rate drawn from this normal distribution. So, one clarification here. The GRT representation is going to give us the mean of this normal distribution, and we're going to represent the variability of that mean as just a free parameter. It's another free parameter. So this normal distribution here isn't directly related to the previous normal distribution.
Dan, can I ask an information question? The way it sounds is that actually you only have one thing going on for trial, that you get lines either a positive, for example, a positive drift rate, or it's in the other tail, it's in the negative, rather than having a race. Is that to be correct?
This assumption, this particular model here, the way that it's set out on the screen here, is a representation you might have for a coactive process. You've got a race between each response, each possible response, but all of the information, you only have one drift rate for each of your dimensions, or one drift rate for your entire object. What I'm going to do in the next few slides is build up a few of these then, and have sets of these racing in parallel or being combined in serial. I think is that what you were getting at? Yeah. So this, even though this looks like we've got two things going on here, this is effectively a single channel process, because you've only got one race between these two responses. What else do I need to tell you about that? Okay, I think we're okay to move on. So the steps that we're going to use in fitting the model are pretty straightforward. We're going to use R to load in a bunch of useful packages, organize the data, and set up the starting parameters for the model. Then we're going to use a simplified version of general recognition theory, which assumes perceptual independence and perceptual separability and decisional separability to derive a drift rate for each channel in the model. Then we're going to simulate response times for each of our channels, and then use the logical rules to combine the response times from different channels. So the way in which we combine those response times from different channels will depend on the particular type of mental architecture that we're interested in using. Now, one thing I did want to point out was, if you just use this time equals distance divided by rate assumption on its own, it's actually a pretty terrible model of response times. The way in which the linear ballistic accumulator improves upon that particular calculation is by assuming that the start point is uniformly distributed on each trial. So every trial, you're starting from a slightly different location. So you tend to start within this range, but it varies uniformly within that range. Your drift rate also varies from trial to trial. So every time you see the same stimulus, you don't get exactly the same drift rate from that stimulus. It's a little bit variable. There are a number of different process assumptions you could make to kind of explain where that variability comes from, but none of them are really directly testable, so this is just an assumption of the model. Whenever you combine this type of variability with this normal drift rate variability, that allows this very simple setup to predict pretty accurate response time distributions. It allows you to explain things like the types of speed accuracy trade-offs that you see, along with the different types of fast and slow error response times. So there's been a lot of work done showing that this is actually a decent model to use. There's been some recent work showing that it is potentially too flexible, and if you don't make specific assumptions about the type of distribution for the drift rate, you can really fit any response time distribution. But we're going to adopt the idea that this particular distribution is a normal distribution, which will allow us to do the calculations we need to do and not have a model which is too flexible. Okay, so I'm going to start up R now and go through some of this preliminary stuff with you. The steps that we're going to do is just do the preliminary stuff, then I'm going to show you how to use the general recognition theory to derive the drift rate for each channel. Then I'm going to show you how to use the linear ballistic accumulator to actually simulate RTs. So I'll show you the analytic expressions for the linear ballistic accumulator, but I want to do it by simulation so you can really see what's going on. And then I'm going to show you how you combine each of those RTs to get out the final predictions. And ideally what you would do is then optimize your parameters using some optimization function so that you can tune the predictions of your model to match the data about as best as you can. And the problem is that if I start that running now, it might not get finished by the time we have to go break for lunch. So I'll show you how to do that, but I'm not actually going to go through and do that. I'm actually going to use parameters which are pretty close to the optimized parameters. Okay, so I'm going to be using something called RStudio, which is just a development environment for R. It's going to look a little bit different from what Joe is using. It basically takes all the windows and puts them into one window. I think probably because I come from a MATLAB background, it reminds me a little bit of where I came from. So I'm going to open the files. The files that you'll need, which will be on the website, are this main test session.r. So this does all the background work. And then there's a bunch of logical rule LBA functions which get loaded in by this package. And those particular functions will be the ones that will be important to kind of work through. And then there's also some test coordinates, which are going to be our coordinates for each of our stimuli, and our test data, which is the data that we're going to fit. So I'll open this file first. Now, is there an easy way to increase the font in RStudio? Can everybody read that okay? Or do you want me to make it a little bigger? I don't know how to make it bigger. That is a false promise. Yeah. Oh, that's a good one. Oh, that's just magnifier. well, wait, maybe I'll zoom in. Here we go. Yes, that's looking a little bigger. Let's go one more. I have 4 eyes. So I've just included some general housekeeping stuff at the beginning to clear the global workspace of variables we created and clear the screen. And then I've listed here all the packages which I've installed. And if you haven't installed these before and you have internet connection, uncommenting these things by removing that hash sign will allow you to install each of these packages. These will just give some useful functions that we're going to use later. I'll then load them all into the library. I actually haven't installed Joe's SMT package yet, and I don't have internet access, so I'll just call them right out. The 2 most important things are once you've got your working directory set, then we need to read in a table which gives us the stimulus coordinates for each of our 9 stimuli. Now, if I show you what this data file looks like, the way in which these are set up is in a slightly peculiar numbering system, which I'm going to blame Mario for. Okay, I will blame Ron. What these numbers represent are the order in which these are entered into the file. And I should put a little note with this because this is not going to make any sense to anybody. Well, it's in our paper, but the numbering of the files is 1 is this stimulus here, which is our stimulus, which is high discriminability from both of these dimensions. Then 2, 3, 4, 5, 6, 7, 8, 9. Now, once you've seen this enough, that's second nature to you. But if you haven't seen it before, you would never guess that that's the way things are numbered. You can, however, work it out by the coordinates that are actually shown here. So this first column of numbers represents the value on the x dimension. The second column of numbers represents the value on the y dimension. And the third column represents the category that the stimulus belongs to. So 1 here indicates that it belongs to category A. 2 indicates that it belongs to category B. So 2, 2 would be, if the stimulus dimensions are numbered 0, 1, and 2, then 2, 2 is the one in the upper right corner. Now, I'm assuming here that each of these stimuli fall on a very particular grid, but that doesn't necessarily have to hold true. And one of the approaches we've taken in the past is to attempt to get some idea about what people's representation of the locations of these stimuli actually are by applying an identification task or a similarity rating task and getting some proximity estimates between these items, and then applying multidimensional scaling to actually uncover a two-dimensional geometric representation of the locations of these items that gives us some indication about, well, how similar do people think these things actually are? So we could apply multidimensional scaling to these and plug in the output of that to get potentially more realistic representation of the item location. But for now, I'm just going to assume that they fall on that particular grid. So in our studio, if I want to load this information in, I can just press Control Enter, and it will run the highlighted section, and now I can access that stimulus variable. Maximize the screen. What I'll do actually so if I type the stim that I get in this matrix with the names of the columns as I've identified them here, so dimension 1, dimension 2, and category. The other important thing is the data. And the data are a long matrix of numbers where the columns of this are explained here in this code. So the first column is the item number, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And the second column is the category it belongs to. The third column is whether it was correct or not, and the fourth column is the response time. So I'm going to go ahead and load those in as well. And I've got a bunch of starting parameters here. These are just good guesses where things might be. And they're not going to make any sense for at the moment for reasons which I'll explain whenever we delve deeper into the models. And then I'm also going to load up this source file, which has all of the functions that we're going to need to fit the models. So let me open that particular file as well. So that main test session.r file packages up everything to send it away to the functions that we're going to need to compute the model predictions and the model fit. And these functions unpack that information and then do stuff to it. So let me explain to you a little bit about what happens inside these functions. So we're sending to these functions our parameters, our stimuli, and our data, and the particular model that we want to fit. So we've got a bunch of different options for the model, and I'll just list them here so you know what they are. These are just choices that you have for the different types of models that you can fit. I've just indicated here that I want to start with a parallel self-terminating model. So since I've loaded that stuff up, I can just go in here and run portions of this function. Now, because I'm simulating the model, and what the optimization code is going to do is tweak these parameters and try to get my predictions to best match my data, I've seeded the random number generator so that given the same parameters, I can get back the same sequence of randomly generated numbers, which will allow some stability in the estimates which are coming out of this particular function. I'm just going to run this information to show you what's going on here and the unpacking of these parameters. So out here in the main file, I've commented these things out, but I've included a number of different ways in which you can optimize parameters from this function. This optim function has a bunch of different possible optimization algorithms that you can use. The default is the Nelder-Mead simplex algorithm, and that's known as fmin search in MATLAB, if you're familiar with that. And it has a bunch of different types of methods you can specify. It tends to work generally well, but it has problems if your parameters are constrained in any way. It likes you to have fully real valued parameters that range from negative infinity to positive infinity. So what I've done out here is actually transform these parameters so that they can take on that range. And then inside the function, I've retransformed them out of that. So if you recall, the positions of our items, our values on each dimension, were 0, 1, and 2. So that location, one of the parameters, or two of the parameters that we have are the locations of those decision boundaries. So jump back to my slideshow. So the locations of these, the means of these distributions are given by that in that coordinates file. So the mean here would be 0, the mean here would be 1, and the mean of this distribution would be 2. And then the other piece of information we need, or one other piece of information, is the location of this decision boundary, and that's going to be a free parameter in the model. So we're just going to, that's going to be one of the parameters that we're going to tune. And that is going to be allowed to move back and forth between 0 and 1. So all I've done is taken a logit transform of that decision boundary parameter so that it can vary between minus and plus infinity, and then I've taken the inverse logit function inside the function to transform it back to between 0 and 1. So if I look at that parameter value inside the function, you can see that it's around 0.5, roughly halfway between the two stimuli. So 0.47 and around 0.45. Those are my two boundaries, the first one on the x dimension and the second one on the y dimension. Another piece of information that we need is what's the variability of these distributions. Once we know where this boundary is and we know the means and the variabilities of these distributions, then we can compute the area in both category A and category B to get our drift rate. So the variability of those dimensions, we're also going to assume that that's a free parameter. We're going to make a simplifying assumption that the variability is constant across all values on a given dimension. So that particular parameter is called S here, and the variability on dimension values for dimension X is 0.68. On dimension Y, it's 0.53. Now that we know those two things, we can go in and actually compute the proportion of area that falls in each of the regions for each of our stimuli. And so that's done in a little bit further down. I'm going to run this code here to show you what it outputs. I've created a function called I haven't defined my model yet, so it wasn't able to run that properly, but I'm just going to define that now. Okay. So I've created a function called GRT-DBT, which will compute the area under those curves. Now, in RStudio, I've listed all these functions one right after another. This isn't nice and tidy like Joe's R package, so you can't just go and go to CRAN and download the logical rules package. Because we want to tweak this model based on different assumptions we want to try out, I've actually programmed each of these functions into R manually. Well, Joe programmed manually too, but there's no a distributed R package for these. So the function for GRT-DBT is actually just listed below the main logical rules LBA function. And this works exactly as you'd expect. It computes the area under those curves. It does so using a bivariate normal cumulative distribution function for the coactive model. So what I've done is divided up these regions into 4 regions. This region up here would be where the category A stimuli fall, and then the category B stimuli fall in these regions. And then you compute the area under the bivariate normal in each of those regions to end up with your drift rate, and then we've truncated the drift rates so they don't equal 1 exactly or 0 exactly, which can cause a little bit of problems. If you don't have a coactive model, then we're not going to use the bivariate normal, we're going to use the univariate normal, which is just the normal cumulative distribution function after we Z transform our means and mean locations of our stimuli. So that gives us an estimate of what proportion of these distributions fall in each of the areas represented by each of our categories. We're going to use that information then to form the rate of processing in the linear ballistic accumulator, and from the linear ballistic accumulator, we're going to sample decision times. So this gives us, this code here will run the GRT-DBT function. This is just pulling out the second and third columns of this matrix, which are our stimulus coordinates. So if I show you what that looks like, you can see that that's numbered each of the items 1 to 9. It's got the stimulus coordinates in the second and third columns and the categories in the fourth column. It also takes an input of our decision boundaries and our perceptual variances. And the default for the number of channels is 1, so its default is a coactive processing model. But if you specify a different model, it will change that number of channels to 2 and to do the right thing inside the function. So this returns to us a series of drift rates in a matrix which I've called VAI for reasons which are opaque to even me. Those are the three letters I was thinking of whenever I was programming this. And what these numbers represent are the drift rates for each of those stimuli. And we can look at those to see whether they make any sense. So these are the probability of, you can think of it as the probability of, or the rate of accumulation of evidence towards category A, towards a category A response. So here are two drift rates, one for dimension X and one for dimension Y, for that high stimulus in the upper right-hand corner. Both of those are very high. So 0.99 and near 1 on dimension Y. This is stimulus number 2, so this is the one underneath it, which is far from the X boundary, but close to the Y boundary. So it has a high drift rate on dimension X and a lower drift rate on dimension Y. If we go down to the category A stimulus, which is close to both boundaries, then it has a lower drift rate on both boundaries. Still pretty high overall, but low in comparison to this high stimulus. And then as we start to move into category B, we can see that for one of those dimensions, the probability of the rate of accumulation towards response A is actually lower than 0.5, meaning it has a higher rate of responding response B, because the rate of responding response B is just 1 minus these probabilities. So this is item 5, which is actually satisfies the A rule on the X dimension, but not on the Y dimension, so it has a higher rate of accumulation on the X dimension and a rate of accumulation on the Y dimension, which actually is pointing towards response B. And then if we go all the way down to the redundant stimulus, the stimulus 9, which satisfies the disjunctive rule on both of those boundaries, both dimensions have a higher rate of accumulation for response B than response A. Okay, so using that information, we can generate some decision times. How are the decision times generated? Well, having received a drift rate, what we need to do is generate decision times for each of the channels in the model. So this is now we've got two channels, one for response A and one for response B. We can see here that our drift rate is a little bit stronger for response A than response B. The kind of angle of that arrow indicating that probability, or that drift rate in the model. And what we need to do is compute what are called the first passage time probabilities for hitting each of these thresholds. So if this were a category A stimulus, and we're looking at now one of the dimensions only, that value on that dimension gives us both a rate of accumulation towards response A and a rate of accumulation towards response B. If it actually falls in the A region, then the correct answer is response A. So we would hope that this distribution would be a little bit faster than this distribution, or a little bit earlier in time. Most of its mass would be earlier in time, because this is actually an incorrect response. This would be represent the error response time distribution for that particular dimensional value. So these are the equations from the Brown and Heathcote paper, and these look difficult, but they're actually pretty easy. These are very easy to program. Each of these things is actually a parameter in the linear ballistic accumulator. So you've got your thresholds for each of your accumulators. So how much evidence do you need before you're willing to say response A? How much do you need for response B? You've got a maximum range of the uniform starting point distribution. You've got your drift rates for each of the accumulators, and the between trial drift rate variability, which we're going to assume is a free parameter. And you've also got something representing the non-decision time, which is just a constant, which is typically referred to in these papers as T0, or T0. And these functions give you the cumulative distribution function and the probability density function for each of the accumulators. So there's one accumulator for each response, and those functions tell you information about these distributions for those accumulators. Now, what we typically want to know, though, for a given dimensional decision, which one of these accumulators finishes first? What's the probability of this accumulator, the response A accumulator, finishing before the response B accumulator. And to work that out, we just take the probability for the response A accumulator and multiply it by the survivor function, so 1 minus the cumulative distribution function for the other accumulator. So basically what we're saying is the probability that that our response A accumulator finishes first is the probability of responding at a particular time from the response A accumulator multiplied by the probability that the response B accumulator hasn't finished yet. So these are really easy. So the LBA is really nice because it has these nice analytic solutions. I'm not going to use them, but if you wanted to use them, they're there. Each channel in the model, so each dimensional decision is represented by a single pair of accumulators. And these encode the race between each response. So you have one pair of accumulators for the coactive stimulus and multiple pairs of accumulators if you have a parallel or a serial model. Now, for a parallel model or a parallel self-terminating model, we just have more accumulators that we're racing against, so the analytic solutions are also very easy. For a serial self-terminating model, we have to take into account which dimensions get processed first, and the convolution of those dimensions if one dimension is processed first followed by another dimension. And that gets a little messy, and I'm not going to talk about that in this particular talk, but there's lots of stuff in the literature on this. I've shown the calculations for the random walk models and other types of sequential sampling models applied directly to this problem in a 2012 paper. So what we're going to do is generate decision times from each channel of the LBA. And we're going to do that using this, the simulated decision time is going to equal the distance we have to travel, which is the threshold minus the starting point, divided by the rate of processing. And we're going to generate a bunch of decision times. So we're going to generate a bunch of random starting points from that uniform distribution, subtract each of them from our threshold to get a bunch of different random distances we have to travel. And then we're going to generate a bunch of random drift rates from a normal distribution, and then divide the distance we have to travel by the drift rate to get a bunch of simulated decision times. So all of that's taken care of in this gen decision time function that I've written down here. So the first thing we're going to do is sample a starting point from a uniform distribution and then reshape it so that it has, so that it's a matrix with 9 rows, each row indicating a particular item that we're sampling from, and then a number of columns equal to the number of simulated response times we want to generate. And I'm going to generate 10,000 response times so we can get a good approximation for what these distributions actually are. So I'm going to use the R unit function, which is built into R, to generate uniform starting points. Then I'm going to generate sample drift rates from a normal distribution, and these are normal random samples using the rnorm function. So these are samples from a standard normal distribution which has a mean of 0 and a standard deviation of 1. So I've got to transform that into the distribution that's actually representing my stimuli. So I just multiply those samples by the estimated perceptual variability and add in the location of each of the items, or rather the drift rate for each of the items to transform those means. I do a little truncation here to make sure that they're not exactly equal to 0 or exactly equal to 1, or actually not greater than 1 or less than 0. And then I compute, this is all done using the probability of responding, or the drift rate for responding with response A, and I just take 1 minus those samples to get the drift rate for response B. I had done this initially using thinking about things in terms of correct responses and error responses, but I changed it to thinking about A responses and B responses because it made more sense. So if the model is a coactive model, we only have to do this once for one pair of accumulators. If it's not a coactive model, we do it twice. In this particular example, one pair of accumulators for each dimension. Then taking our whole matrix of random samples, we then convert these start points and these drift rates to time using that time equals distance divided by rate calculation. So we get a sample, a matrix of times here for our A accumulator on channel 1, and a matrix of times for our A accumulator on channel 2. So this is just now the threshold. What I'm doing is I'm replicating that threshold 10,000 times for each item, subtracting off the starting point to get our distance we have to travel, and then dividing it by the drift rate to get an estimate of the time that it takes to get there. If the model's not coactive, we do this twice, otherwise we don't worry about the second channel, and then we return all of those sampled response times. So far, all the models are exactly the same, with the exception that if it's not a coactive model, we do everything, we repeat everything for the second accumulator. So if I can show you what these samples look like. I'll just pull out a small set of the samples. I'll just do 10 of them. So this is now, well, let me just do 5, because I made my font a little bigger. This is now 5 sampled response times in seconds for stimulus number 1, stimulus number 2, 3, 4, 5, 6, 7, 8, and so on, for the time it takes them to reach the threshold for response A. So it's responding category A. For the first accumulator, we can also look at the times for response B. Now, let me just pull out stimulus number 1 here, because it's informative to look at what's going on for an actual A decision. So this stimulus is a category A stimulus. The values that it has on each dimension point you very strongly towards category A. And these are the values that you get on each of the accumulators. So the numbers for reaching the A boundary, the A threshold, are quite sensible. So 638 milliseconds, 617 milliseconds, 858. But the times for reaching the B threshold are much larger. So 4 seconds, 5 seconds. Oh no, that's actually much larger than 5 seconds. That's extremely large. 7 seconds, another extremely large sample. So for this particular channel, you're getting really strong evidence that it belongs to category A. You reach that A boundary much faster than you reach the B boundary. In fact, the A boundary tends to beat the B boundary most of the time. Only in a very rare occasion is the B boundary going to beat the A boundary in these samples. If we look at an alternative stimulus, though, so let's look at now stimulus number 9. Now the B, this stimulus actually belongs to category B. The values on the first channel, dimension X, have higher drift rates for dimension for the B decision than the A decision. So the sample times tend to be much faster for the B decision than the A decision. They're not astronomically faster because it's still close to both of those boundaries, whereas that high stimulus is really far from both of them, so that very high drift rates for category A. Okay, so just the last little thing we need to do here before we get to our predictions is actually combine these drift rates, or combine these sampled response times according to the model we want to use. So if it's a coactive model, all we need to do is work out whether the A accumulator finished first or the B accumulator finished first. And if I scroll back up here to my main function, I've generated the sampled response times. I can now organize the results according to the model and add in the non-decision time. And this will give me, this will pull out the correct RTs. So this correct RTs takes in the model as a parameter and uses that to determine how it combines the information from each of the channels. So what does it do? Well, it just takes the times from each of those channels and counts up how many samples were faster for the A accumulator than the B accumulator. So if the correct decision is category A, then it counts out the proportion of those 10,000 samples for which the A accumulator finished before the B accumulator. And that gives us a representation of our target response times. It does some other tidying up of things to make things easy to understand by giving each of our samples an index according to the number, but that's not crucial. For a contrast category, for a coactive model, it counts up how many of them were faster for the B accumulator than the A accumulator. So the coactive model is very simple to understand. You just compare the two sample response times from each accumulator and see which one is faster. We're using a parallel self-terminating model. This is a little bit more complex. We're just doing the same thing again, comparing which one was faster, but now there's a few different ways. Well, there's one way in which a target item can be correct. The sample times on the first channel for the A accumulator need to be faster than the sampled response times on the first channel from the B accumulator. That has to be true for both the first channel and the second channel. So what we do is we just check, we create a logical index, which is true if the sampled response times are faster on the A accumulator and then the B accumulator on channel 1. And using this logical operator, we also looked that they're faster on channel 2 than on A than on B. Then we pull out those samples for which that's true, and that gives us the total set of target response time samples which were actually correct. We could do the same thing for the errors. I haven't done so here, but it's straightforward to do so. We just check if any of the B, we pull out all the samples for which the B accumulator is faster than the A accumulator on either channel. Those would be incorrect predictions, or they would be samples for which the response to this particular A item was incorrect. For the contrast category, there's a bunch of different ways in which you can be correct. You can be correct if both of your B accumulators finish before the A accumulators, or you can be correct if only one of them finishes before the A accumulators. So we check whether both of those things are true, or whether only one of those things are true. So there's only one of the B accumulators there. What's important is the way in which we compute the response time depends on which one of these situations we're in, which one of these states we're in. So if both of those channels are correct, so if both of the B accumulators are faster than the A accumulators on both channels, then the decision time is the minimum time of both of those sample RTs. So having done that comparison, then we go in and apply the minimum function to our samples for which that's true. That's all the way out here at the end, and that pulls out the minimum response time sample from that pair of samples. The other way in which we can be correct for a category B stimulus is if only one of the things finishes first. So we check whether one of the B accumulators has beat the A accumulator on one of the channels. And if that happens to be true, then the response time for those particular samples which are in that state is just the response time of the B accumulator. And so what this code does is pull out those instances and assign the response time to those samples correctly, and then combine them into a big matrix called correct RTs, which it outputs. So this function does all the work for the logical rule models, is get correct RTs. So it has comparisons to pull out the correct RTs for the coactive model, the target RTs, and the contrast category for the coactive model, the parallel self-terminating model. So the target RT samples here are given by the maximum time, so it applies the maximum time to those samples. In any case where the A accumulator was faster than the B accumulator on both dimensions. And goes through the contrast category items as well. It also has the parallel exhaustive model. So there are a number of different states you can be in to be correct and wrong in these cases. The serial self-terminating model For the serial self-terminating model, if you want to run this, you have to input a 10th parameter. So there's another parameter which gives you the probability with which you, the probability or the proportion of trials on which you process dimension X before dimension Y. So that's another parameter which is input to the model. And it goes through and pulls out all of the states for which you can be correct for each of the items and each of the categories. And the zero exhaustive model applies the sum of the response times, regardless of whether the A accumulator finishes before the B accumulator or vice versa or both. So all of the 5 basic models are there in this code, and you can generate predictions for each of those 5 models. I haven't gone into any of the more complicated models, but the code is fairly easy to modify once you read through the notes and kind of get a sense about what's going on. So if you want to try out new things, it's not difficult to do. So once you've gotten the correct RTs and added in the non-decision time, then the last bit of the code computes how well does your predictions from your model fit the data. And there are a lot of different ways to do this. If you're using the analytic solutions to the LBA, what's really nice about them is they actually give you the likelihood for observing each response time. So you can just compute the probability of each of your RTs given that particular model. Because I'm trying to stay somewhat close to the logical rule models paper, we use the quantile maximum likelihood estimate, which isn't really a likelihood at all, but it functions much like a likelihood. And the way it works is you take your data, you carve it up into quantiles, so we find the 10% RT, the 30%, 50%, 70%, and 90% RT, and then we take our samples and see which bin they fall into between those RTs. And we expect that if our model is fitting our data well, that 10% of our sampled predictions should fall before that 10% quantile, and 20% should fall between 10% and 30%, and then 20% between 30 and 50, and so on. And we use a multinomial likelihood function to compare our predictions, so our binned sampled response times, to our expected data quantiles to get a measure of the fit. And I'm not going to go through those functions, but there's some debate in the literature about whether this is a good thing to do or not, because quantile maximum likelihood estimates aren't a real likelihood, but you can nonetheless, we've done it both ways, and it tends not to make much of a difference, at least for fitting these models. So this will give you a likelihood, and the optimization function is trying to find the maximum likelihood, but it does this by minimizing the negative likelihood. And in fact, it minimizes the negative log likelihood, so I've just computed the quantile maximum likelihood estimate and then negated it. And then there's some other tidying up functions to make sure that all of these aren't crucial to the model, but they help translate my MATLAB code into R accurately. This function is not used by the model, but it's extremely useful, so I've copied it in here for future reference. And then the last thing we do is plot the data. So it's just about lunchtime, so why don't I show you the types of plots you get out of this. I'm not going to optimize it. I've included the optim function here to fit tri-simplex search or the Nelder-Mead algorithm, or you can specify other types of algorithms. I've also included this particle swarm optimization search, which tends to be preferred by Chris Duncan, for instance, who is, uses the LBA model quite a bit in his work. So let me show you what this does. If we just start with some parameters and the margins too large. Let's try again. Okay, there we go. So this is fitting the parallel self-terminating model to this particular data that I've specified from each of these items. And we actually get a fit value returned of 184.79. This is the quantile maximum likelihood estimate. That's actually not too bad. If you have a really bad fit, it can be up around 20,000. So you know you're nowhere close. And if you look at these distributions, you can see that most of the time they do a good job. So here, the prediction for this item is highly accurate. It's really nailing that distribution. But some of the times it's not doing that hot at all. So here it's predicting more fast response times than are actually seen in the data. Here it's predicting more long response times than are actually seen in the data. But on the whole, it's across all 9 of those items, it's not doing too bad of a job. And how can you tell how well it's doing in comparison to another model? Well, let's try another model, let's try the parallel exhaustive model. So remember, our fit for that model was 184. Our fit for this model is much worse, 469. Now we can take those values and go away and compute something like the Bayesian information criterion to get a sense about which one of those models fits better, taking into account not only how well it fits, but also the complexity of the model in terms of the number of parameters. Both of those models have the same number of parameters, so in this case it turns out that the model which has the lower fit value is actually the one that's going to win in the VIC comparison, which is going to be the parallel self-terminating model. You can look at the fits and you can see that overall the parallel exhaustive model is not noticeably doing much worse, but if you start to really look into it, you can see that it's missing in a few key places, potentially more places than were missed by the parallel self-terminating model. So I'm going to stop there with a few minutes left for anybody to ask me any questions. I'll give this code to Cheng Ta for you to go in and play around with. Feel free to email me any questions you might have. I'd be happy to know where I've done something wrong or where you think you've got a better idea for how to do it, because, as I mentioned, I'm also new to using this program. Thank you very much. Everyone's ready for lunch.
You find that it's really powerful work. You found that I should say the complement prep powerful work. You find that the conclusions about the major features like relevance, serial, stopping rule, and so forth, do your simulations and so forth indicate that certain kinds of, for example, the specificities of whether you use a random model or the LBA or something else affects those kind of really major conclusions, or are they robust across different kind of particulars of the distribution?
The architectural predictions are differential enough that the actual sequential sampling model assumptions don't seem to affect them too much. So you get very clear distinctions between, if things are truly parallel, so if I generate the data from a parallel model, then it doesn't matter whether I use a random walk then to try to pick up on the underlying architecture. It can tease apart pull out the appropriate model. So there doesn't seem to be any effect of whether you're using a discrete sequential sampling model or a continuous time sequential sampling model. As you know, there's a huge debate in the literature about whether you need the type of within-trial variability that, say, the linear diffusion model offers, but the linear ballistic accumulator doesn't. That doesn't seem to make any difference for the type of questions that we're asking.
Good. Excellent.
So the way your code is written, it seems like it would be fairly easy to look at violations of perceptual independence and perceptual separability to allow those to be free parameters in the model. Do you know if they're identifiable, and if they are, play around with them at all?
Great questions. So yes, the code is easily modifiable to start to look at violations of perceptual separability, perceptual independence, and decisional separability in these models. Whether or not they're identifiable, I think, falls under the same considerations that all the recent work showing that, in fact, they might not be I don't think tacking the distributions or the response time model onto the end of it solves that problem. Now, I have looked at this, however, but have made a few simplifying assumptions. Incidentally, I would say that I thought a lot of the debate in the literature about whether perceptual separability and decisional separability were identifiable applied to cases where you wanted to use something like the D prime analysis on those dimensions, or does it also apply if you're fitting the model? You might know this a little better. It also applies there. Okay, good. What we've done in some of our work and some recent work, which we're writing up at the moment, is attempt to get some independent evidence about what the type of violation of perceptual separability might look like by using a multi-dimensional scaling solution, and what the violation of decisional separability might look like by allowing either orthogonal decisional boundaries or optimal responding. So we've looked at fitting each of these models, so all the big five of SFT, along with particular assumptions in the stimulus representation. So we fit all five, assuming both perceptual separability and decisional separability. And then again, assuming that there was the multidimensional scaling representation gave us a good handle on the violation of perceptual separability, mean shift integrality. And then assuming either mean shift integrality along with decisional separability or optimal responding. So we fit, three different assumptions for the perceptual representation and five different assumptions for the processing architecture. And we found very clear individual differences for which one of these models fit better. But this was a kind of a first step towards exploring that kind of idea, combining both the mental architectures with more complicated perceptual representations for the scaling.
Two questions. The first one is a clarification question. Could you explain how many parameters are there in each model, and what are these?
Great question. I skipped over that.
Yes.
I apologize for that.
And the second one is, how do we simulate a mixture model between serial and paired model? Using this.
My R session aborted itself, but it brought itself back, so if I can get in here, I can show you the parameters. So I mentioned two of the parameters were the locations of the decision boundaries, and another two were the variability of the perceptual representations of those stimuli. So that's four parameters. So I mentioned that these were transformed. These are transformed so they lie between 0 and 1, so they fall between those two items. These were log transformed because they have the same. So the GRT representation has four parameters here, but of course if you move to more complicated GRT representations, you could increase the number of parameters to get at those more complicated representations. So if you could think about having an orientation and an offset if you wanted to allow for violations of decisional separability. It could also allow for different types of thresholds. In this particular instantiation, though, there's only the decision boundaries and the variability. The LBA, the kind of back end of the model, has an additional 5 parameters. I've assumed that the starting point for each of the accumulators has the same range. I've also assumed that the thresholds can be different between the A response and the B response, so you allow for different biases between those two categories. But when you have multiple channels, those thresholds are the same between the channels then. There's the between trial drift rate variability, this VS parameter, so that's an additional parameter, and then there's the non-decision time parameter. So there's 9 parameters in total for all of the models except for the serial self-terminating model. For the serial self-terminating model is an additional parameter, which is the probability that you process dimension X before dimension Y. So that's a 10th parameter in that model.
What is VCI?
VCI is one of the bugs that I corrected before I sent you the files, or after I sent you the files last night. That's now become VAI and here. So that was a hangover from when I was thinking about these things in terms of corrects and errors rather than A's and B's. So I'll send you the new code, and some of that stuff will fit together a little better. The second question was, how do you fit the mixture model? And I haven't programmed it here, but it's very straightforward. There's an 11th parameter that you need, which is the probability the given trial is going to be a serial process versus a parallel process. And then you, for this particular setup, what you would do is sample a number of samples from the serial process in proportion to that probability. So if you had 50-50 mixture, then you'd sample 5,000 from the serial process and another 5,000 from the parallel process, and those would just be your samples for those distributions. So I've set that up in my MATLAB code, but I haven't translated it over to R yet. But that's certainly something we could do, because that seems to be a model which comes out again and again as being a potentially good model for processing separable dimension stimuli where the dimensions are in the same spatial location. So it's a theoretically interesting model, probably should belong to this, this set of functions.
If no further questions, I think it's time for us to thank Professor Little and start with the handout session.
Thank you for your participation.